In fluid dynamics, there exists an important relationship, an important equation known as Bernoulli's equation. And Bernoulli's equation basically states that when we're talking about a moving fluid, where the velocity is low in that fluid, the pressure is high. And where the velocity is high within that fluid, the pressure is low. So let's suppose we have the following fluid that is moving within the following pipe. So let's suppose the left side of the pipe is 0.1 and the right side is 0.2. Now, the cross-sectional area of the pipe at the left side at 0.1 is A1, and the cross-sectional area on the right side of the pipe is A2. Now, notice, because the cross-sectional area on the left side, A1, is higher than the cross-sectional area of the pipe on the right side, because A1 is greater than A2, then due to the equation of continuity, we know that the velocity of the fluid V1 on the left side is lower than the velocity of the fluid on the right side, V2. So V1 is smaller than V2 because A1 is larger than A2. And basically what Bernoulli's equation tells us is where we have a lower velocity, we must have a higher pressure. And where we have a higher velocity, we must have a lower pressure. Now, Bernoulli's equation also can be stated in equation form. And in order to derive our equation, let's make the following assumption. Assumption number one is that the fluid we're looking at is undergoing laminar or streamlined flow. Assumption number two states that our fluid is incompressible, which means that we have constant density. And our assumption number three states that our fluid has no viscosity while it's moving. So, let's begin by looking at the following two diagrams. Let's suppose we take the following pipe and we take a certain volume of the fluid shown by the following blue region, and our fluid moves from point A, from point 1 to point 2. So point 1 is given by diagram A and point 2 is given with diagram B. Point 1 begins in this region and point 2 begins in this region. So notice that our entire blue volume of fluid moves from 1 to 2, and it moves a distance of change in L1 on the left side, and it moves a change in distance L2 on the right side. Now, also notice that the distance from the ground to the position 1 is y1, and the vertical distance from the ground to position 2 is given by y2. So we basically want to calculate how much work is required to move a volume of fluid shown in blue, this blue volume, from position in diagram A to position in diagram B. Also notice fluid entering cross-sectional area A1 travels a distance of change in L1 and forces the fluid at cross-sectional area A2 to move a distance of change in L2. So this fluid is being pushed by a fluid found to the left of point 1. And this fluid in turn pushes the fluid here to move a distance of change in L2. So, let's begin by calculating how much work is done on the fluid at cross-sectional area A1 by the fluid to the left of cross-sectional area A1. So once again, there is a fluid that exists to the left of point 1, which is not drawn, that actually forces this fluid to move to point 2. And we want to calculate how much work is required to move that fluid. So let's say work 1 is that work we're trying to find, and that means it equals to the force acting on cross-sectional area A1 at point 1. So let's call that F1. multiplied by the displacement, because work is equal to force times displacement. And in this case, our displacement on the left side is change in L1. So force 1 multiplied by change in L1. And force is simply pressure times area. So force 1 is equal to pressure at point 1 multiplied by cross-sectional area at point 1 multiplied by displacement change in L1. So once again, this quantity is how much work is done on the fluid at point 1 by the fluid to the left of point 1. Now let's look at 2. Now we want to find how much work is done on fluid at point 2 at cross-sectional area A2. Now notice this work that is done is negative. And that's because the force that acts is opposite to the motion of our fluid. So work 2 is equal to negative of force 2 multiplied by change in distance L2. So our displacement along this section, along the right section of the pipe, is change in L2. So once again, force 2 is equal to P2 multiplied by A2, and this is exactly what we have. Now, there's also the work that needs to be done against the force of gravity. So that means this work, let's call it work 3, will also be negative. So we have work 3, the work that needs to be done by the fluid against the force of gravity, negative m times g, where the m is simply the mass of this entire region of fluid, multiplied by y2 minus y1, where y2 is simply the vertical distance 2.2 from the ground, and y1 is simply the vertical distance from the ground 2.1. So let's say that y2 minus y1 is simply change in y. It's the change between point 1, it's the vertical distance between point 1 and point 2 shown by this region. So once again, W3 is the work done against force of gravity to move our volume a distance, a vertical distance of change in y. Now, let's actually find the total work done. The total work done is simply work total is equal to W1 plus W2 plus W3. Now, recall the work energy principle. The work energy principle basically states that the total kinetic energy of our system, the change in kinetic energy of our system, is equal to the work done on that system. And the change in kinetic energy is given by this equation. 1/2 m, the mass of the volume, times the velocity of the fluid at point 2 squared minus 1/2 m times V1 squared, where V1 is simply the velocity of the fluid at point 1. And this entire kinetic energy, change in kinetic energy, is equal to the total work done. And this is known as the work energy principle. So, recall that the mass of a fluid is simply equal to the density of that fluid multiplied by the volume. And the density of the fluid, let's say, is rho. And the volume of the fluid, let's say, is V, capital V. So that means we can replace mass with rho, the density times the volume, and mass with the density times the volume. And notice mass also appears on the last term, so on the gravitational work term. So this mass becomes our rho times V, capital V, the volume. Now notice that so we have our area multiplied by our change in L1. So the cross-sectional area at point 1 times the change in distance L1 is simply the volume. And likewise, this quantity also represents the volume. And these two volumes are the same exact volume, because the volume that moves this distance is the same volume that moves this distance. So this volume equals this volume. So now we have volume, 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 and volume appear on every single term. And in fact, we can cancel those terms out. And if we rearrange our equation and bring all the 1 terms to the left side and the two terms to the right side, we get the following result. And this result is known as Bernoulli's equation. And notice, because we used the work-energy principle, we can deduce that Bernoulli's equation is essentially derived using the conservation of energy, using the work-energy principle. And this equation becomes very handy when we want to calculate, for example, the velocity of the fluid at point 2, knowing every other variable in this equation. For example, the density of the fluid, velocity at point 1, the pressure at point 1 and point 2, as well as our distances. If we know those quantities, we can calculate using our equation the velocity of the fluid at point 2, of course, making all these assumptions. So Bernoulli's equation only holds when we have these three assumptions.